Yes, welcome back to our YouTube channel. In this video, we are going to discuss about the assigned cookies, where we are initially given with an array called G and also an array called S, where G of I refers to the minimum size of the cookie that the child will contain, and another array is called S, where S of J will represent the size of the jth cookie, and we are going to check that if S of J is greater than the G of I, then that respected cookie can assign to this G of I person, or you can say the child. For example, let me walk you through the example. In this example, the 0th index cookie is of size 1, and this size 1 can be only assigned to the child who have the requirement lesser than the current one, like lesser than or equal to the 1. Now who are the childs that have the same thing? Only this child, right? Therefore I can assign this respected cookie to this person. Got it? And now when I come to here, I again have the cookie size as 1, but if you see that every children is demanding a cookie size greater than 2 and also a greater than 3, but we have a cookie size of 1, so we cannot distribute them to none of them. Therefore we're gonna do nothing, and we have to return at the end, we have to return the maximum number of cookies that can be distributed to the children. Got it? Now here in this case, we are going to only distributing the one cookie. Our output will be 1. Let's try to understand the brute force solution for this problem. If I'm at index 0 and this child is demanding a cookie of size 1, and the minimum size of the cookie to get accepted is 1 itself, right? Here the 2 itself, here 3 itself. Got it? And it can go up to a big number, where in the constants the maximum element that element can take is 2 power of 31 minus 1. Therefore we're going to start from the number itself, 1 itself, and go still to power of 31. And let's check here. The 1 for 1, what is the minimum acceptable size cookie is 1. Does it present in the size, you can say the array S? Yeah, it does present. Therefore I have to increment the cookie, and they noted that we should only use the respected cookie for only once. Therefore we should remove it. Now our S becomes this. Got it? And we are done with this, and I'm gonna move forward. And when I'm at 2, the minimum size to get this child happy, or you can say that to make this child get a cookie, is 2. And does 2 present in the S? No, it doesn't. And what is the upper bound for this? The upper bound is 2 power of 31. We're gonna check for these elements present or not in the S, right? If it's not, then we are done. We're gonna move it forward. And for 3, what is the minimum cookie size itself? It is 3, and it also goes to 2 power of 31. And in this way we are going to do for each and every element present, or you can say each and every child present in the G. And let's roughly analyze the time complexity. It can go from n cross 2 power of 31 for each and every child. We're going to try calculating, or you can say try checking, but I forgot to mention that we're going to try to see in S, right? If I am using a set, it's going to take a time complex of order of 1, but if it is in S, again it's going to take a time complex of order of n, very very huge. So in order to skip this entire computations, we can discuss a better solution for this. Solution for this problem can be figured out using a greedy approach, which is by sorting the both G and S. Now let's take 2 pointers, one at here and one at here, and I'll let you know why I'm taking the pointers. Now the condition given in the problem description is a child can receive the, or you can say can get a cookie whenever the required cookie size should be greater than what the child is expecting, or you can say greater than equal to. Got it? And if the child is want the cookie of 1, the other cookie, if a child expecting a cookie of size 1, then the cookie from the S array should be greater than or equal to whatever he is asking for. Here I can directly say that from the constraints, the G of I should be lesser than or equal to S of J. Got it? Now here we can see that 1 is lesser than or equal to 1. We can assign him a cookie. Got it? Then I have to move the both pointers simultaneously. Now see that 3 lesser than or equal to 2. Does it? No. Therefore I cannot assign a cookie to this respected child. Now what should I do? The thing is, as the elements are sorted in ascending order, we always know that the next element will be greater, right? Therefore we're going to move the j pointer towards right. Now see, 3 is less than or equal to 3. Makes sense? Therefore again the count incremented from 1 to 2. Again move the pointers respectively, right? Now see, 4 is lesser than or equal to j. You can say 6. It's true. Therefore again our count will be incremented. And same. Now the j will goes out of bounds and our program exits, and we return whatever we have as the count, which is 3. And now 3 stands for the maximum number of cookies that we can assign from the array S to the array G. But if this makes sense, then let us quickly write the pseudocode for this approach. Initially we need to sort both the arrays. You can do it either by sorting the given input, or you can take another variable and assign the same arrays to it and sort. And I'm gonna put the two pointers I equal to 0 and j equal to 0, and while I is lesser than the length of g and j is lesser than the length of s, we're gonna do whenever I also take the count variable which is 0, I only iterate, or you can say I only increment the count if g of I lesser than the s of j. In this case please increment the count and at the same time increment the I and also increment the j. Or else if we found that if g of I is 3 and s of j is 2, now in this case we're gonna move it forward. The j pointer should be moved and the I pointer should be placed as it is, right? Therefore we're gonna only increment the j, and at the end just return count. And you can remove this duplicate thing and just write j++, because irrespective of the condition statements it's gonna execute. At every time we're gonna increment the j, right? And that's it. And let's quickly discuss the time and space complexity for this approach. If you see it here, the sorting takes, let's consider the g have a size of n and s as a size of m. It takes a time complexity of order of n log n, and it does takes a time complexity of m log m, and here it takes a time complexity of order of m plus n, and that's it. And what is the space complexity? We have used order of 1. You can say that if your sorting requires a space, we don't consider it here because our algorithm is not trying to use any external space. Solve this in the LeetCode. We're gonna sort both the arrays, and we're gonna take the two pointers I and j, and I'm gonna also take the count variable which is initially set to 0 and start iterating from 0 and goes till the length of g, and the j pointer goes till the length of s. And if the g of I is lesser than or equal to s of j, then in this case we are good to go. We should increment the count and at the same time to also increment the j pointer. Else in this case, when the g of I is greater than the s of j, in that case we're gonna only move the j pointer, and at the end just gonna return the count itself. And let's run it. Okay, then submit this, and it gets accepted. And let's quickly see the complexity analysis. I can say that it's the better complexity. Here you can see that's n log n plus m log m, the same thing that we have discussed earlier, and it's the already optimal. And yeah, that's it. If you really like this video, then please do like, share and subscribe. Thank you.